Alright, this is about a circuit that can fight its own self. Any circuit that you have ever built in your laboratory session has this ability to fight its own self, to oppose its own self whenever there are any changes in the current that is running through it. And we can quantify this quality, and we express that in terms of self inductance L, and the word self is enough. The circuit is beating its own self. It is opposing its own self. Oersted discovered by accident electric current creates magnetic fields around. Actually, he was demonstrating the heating effects of a very high current to his students, and he noticed a needle compass next to the wire got deflected. And that wouldn't have happened without the presence of a magnetic field. And so he concluded that the electric current through the wire creates magnetic fields around. And if you had a straight wire and you run current on it, it creates magnetic fields that circles around the wire, something like so. And if you take those needle compasses and you throw them around in this magnetic field, they will be aligned in the direction of field lines. North pole here, south pole there. And if you take one of those and put here, it will be aligned like that. If you had a solenoid is just a wire wrapped around many times. 1,000 times, 3,000 times, doesn't matter, just wrapped around, just a wire. And if you run current on it, by the way, this is a closed circuit, it creates magnetic fields inside the solenoid, like that. And so if you have any circuit and you run current on it, you create magnetic field. And if the currents are changing, then the magnetic fields are changing. It also means magnetic flux is also changing through those surfaces which are associated with those loops. And now Henry will tell you, Faraday will tell you, there will be an induced EMF in this circuit that fights the change in the flux. They did a lot of experiment and they discovered the phenomena of electromagnetic induction. And this phenomena, this very discovery, runs our economy. We get power in our home because of this law. The magnetic flux that is produced by the circuit is always proportional to the current. You double the current, magnetic field doubles. It also doubles the flux. By the way, flux is defined as the integral of B dot dA, and dA is all those little bit of areas for those surfaces that I was talking about. So this is really the proportionality constant that we call L. And if currents are changing, then the flux are changing. Then induced EMF in this circuit will be minus d phi dt. And that's Faraday's law for you. So this becomes minus L di dt. This minus sign is the consequence of Lenz's law. It tells you the direction of induced EMF will be such that it opposes the change in the flux. So if the current was dying, it means a growing flux through the surfaces, this induced EMF will fight the growth. It doesn't want it to grow that easily. And if the current was decaying, a decaying flux through the surfaces also means that this induced EMF now will oppose the decay. It wouldn't let it die that easily, that flux. This self-inductance L is not a function of the current. It's just a matter of geometry, and I can show you that for the solenoid that we have here. Well, I need some room. My solenoid has capital N loops, those windings. Each loop has radius R, and the solenoid has a length of L, so it's this big. I will also define little n, which is the number of loops per unit length. So capital N becomes n times L, because if you have so many loops in per unit length, and if you have length L, your capital N becomes n times L. Oh, that's easy. This magnetic field is going through all those surfaces. It is penetrating through all those surfaces, and one single surface, which is really circular in this case, has the area of pi r squared, and this flux goes through all those surfaces. So it goes through capital N times pi r squared areas, and I want to find the flux. So your flux is this magnetic field that is going to penetrate through all those surfaces, which is, oh, by the way, I hope you know this magnetic field is given by mu 0 times n times I for the solenoid. It can be calculated using Ampere's law. It's really easy. And if you don't know that, it's alright. Take my word. So this flux becomes mu 0 times n times I times all those surfaces area, which is capital N, and for that I will write n times L times pi r squared. That's it, and I hope you can see that already. It is mu 0 times n squared, we have 2n right now, pi r squared times L, and you have I, and that's the definition is the Li. And so this is pure geometry that the self-inductance has. Look, it has L, that's the length of the solenoid. It has R, which is just the radius of the loops, and you have pi, and you have N, which is the number of loops per unit length, and it goes for n squared, and this is also a constant. And this is really crazy, even to think about it. It's really strange that something can find its own self just because it has some geometry. And I don't understand really. Evidently, the self-inductance is not a function of the current. Even if you take just one loop, whether it is square or triangle or just the circle, it will always have some finite value for L, for self-inductance. Sometimes it's too small that we ignore it, we don't need them. Sometimes they are nanohenry, microhenry, and we don't need that, so we ignore that. But it's never zero. L is never zero. Any circuit that you have is capable of finding its own flux that is changing through the surface that is associated with those loops, with that loop. And now I want to show you the consequences of having a self-inductance in a circuit. And I will start simple. I have a battery with voltage V, and then I have a switch, then I have a solenoid which we call inductor now with self-inductance L, then I have a resistance in the series with resistance R, and as I close the switch, when there is no current running, what I mean is at time t equals 0, there is no current in the circuit. But as I close the switch, current wants to increase, it wants to grow. But there's a self-inductor here that says, tough luck. I hate the changes in the flux, in the currents. I will have to find you. Not find you, I will have to fight you. Length is low. So the self-inductance is fighting the current that wants to run through it, that wants to change through it. But there comes a time that self-inductance loses the fight if you wait long enough, then your current has reached its maximum value that you can find using Ohm's law. Because it becomes I max, then becomes V over R. Because your self-inductance has no resistance. Think of it, it's made of superconducting wire. It's just a wire wrapped around many times. Just a wire. It has no resistance, and that's the definition for pure inductor. It has no resistance. What you can do now is you can make a plot the current's behavior as a function of time intuitively. If you try that, your current as a function of time, I as a function of time, what was happening is you started off with zero current, then current wants to increase, but self-inductor is fighting it, and then it grows slowly and reaches its maximum value until self-inductor loses the fight, and then it becomes maximum, which is given by Ohm's law. And how slowly does it climb depends on the value of the self-inductor, depends on the value of self-inductance. If you have a large solenoid, it will climb up slowly, like so. If you had a small solenoid, it might come pretty fast. If the self-inductance were zero, which doesn't exist really, because I just told you any circuit would have a finite value for L. But if it was zero, the current would have come instantaneously to its maximum value. It wouldn't happen. Every circuit is capable of fighting its own magnetic flux that is changing through the surface. And now you may ask, why does it fight? What's the meaning of fight? Why fight in the first place? What is happening in the circuit? Why don't we get a current instantaneously to its maximum value? Well, the way I think of it is you have a chemical energy here, and as you close the switch, it wants to go into electric energy that will be responsible for the current. But there is an inductor here that can steal the sum of that chemical energy and store it in form of magnetic energy in the field. And so what's happening in the starting is you do not get maximum current all of a sudden. Rather, if you had a bulb here and as you close the switch, your bulb lights up slowly to its maximum brightness. So in the starting, your chemical energy splits into two parts. The one goes into electric energy and some part of it goes into magnetic energy to be stored. And once self-inductor has stored enough magnetic energy, its belly is full now, no more room left for more energy. Now your chemical energy can go into electric energy for the maximum current, and you will get maximum current that you can find using Ohm's law. That's what is happening. And you may ask how much a self-inductor can store energy. Well, it depends on the value of L. If you have a large solenoid, it may store a lot of energy, and it might take a lot of time, of course. And that's why there was a delay in the current. It was storing energy. It was coming slowly. Now, I want to do it mathematically, that this is the plot you will get. And for that, I will have to set up an equation. And if you go into your book, they will advise you to use Kirchhoff's loop rule. That tells you the integral of E dot dl around the closed loop is 0. How can it be 0? You have a changing magnetic field now, a changing magnetic flux. And that's the application for Faraday's law. The integral of E dot dl around the loop is no longer 0. The closed loop integral of E dot dl is minus di, not di dt, of course, dt at the time derivative of the flux, which is b dot da, and this is also minus l di dt. And you have to do this integral over the closed loop, and you have to take this integral over the open surface, and that's the law you have to use. Kirchhoff's loop rule holds for conservative electric fields. Now you are no longer dealing with conservative fields. You have non-conservative electric fields because you have changing magnetic field. So this is the law you have to apply to set up an equation for this. As I close the switch, current will flow. This is the positive side of the battery, that's the negative side. Not the magnetic field, the electric field inside the battery is in this direction. The electric field inside the solenoid is zero. It is zero because it is a superconducting wire, it has no resistance, and there is never any electric field inside the superconducting wire. It is zero. Now current is flowing like so, so the electric field inside the resistor is in this direction, and now I am ready, I am equipped with all the things. I have to do the closed loop integral of E dot dl around the loop. I will start here and I move like so. In going from this point to this point, the integral of E dot dl is 0. It is 0, and this is where the books are wrong. They lie to you. Look, this is 0 because E itself is 0. It's staring at your face. It is 0. Don't trust your book. Even books lies. Now I go through the resistor. The integral of E dot dl in going from this point to this point is IR, that you can find using Ohm's law. This is IR, and now you go from here to here, the integral of E dot dl. You are going up and your electric field is down, so it is minus V. And now Faraday will tell you, Walter Lewin will tell you, this is not 0, this is minus L di dt. And that's the only way to do it. That's the right way. In your books, they do wrong physics. They manipulate this section. You could write it a little differently. You could take V there. V minus L di dt is IR. And this might give you some feeling because you have the voltage of the battery and this is the induced EMF. So what you can get out of it, you could say your induced EMF with the minus sign is opposing the voltage of the battery, and that's the Lenz's law. That's all about the Lenz law. It is opposing the voltage of my battery, this induced EMF. And so this is the differential equation I have to solve. And to solve it, it's really easy. It's even given in many books. I will give you the solution. The current as a function of the time is the Imax times 1 minus e to the minus r over L times t. And I have to check it if that's right. Check at time t equals 0, you must have 0 current. Put 0 here, it becomes 1 minus 1, and yeah, your current at time t equal is 0. Of course, you will find that, check that. As you wait long enough, as the time goes to infinity, your current must have reached its maximum value. And it should have been, put infinity here, it becomes 1 minus 1 over infinity, and so yes, your current becomes I max, which is V over R. It's given already. If you wait L over R seconds, put here L over R seconds, you get 1 minus 1 over E, and it will give you your current becomes 63%. Is it 63%? Yes, of your I max. What I mean is, at L over R seconds, your current becomes 63% of your I max. That's what it is about. Look, the didt here, the slope is steeper here than that. In the beginning, it is steeper than if you had waited longer. It means your self-inductance is capable of fighting you harder in the beginning. Then as you wait long enough, after a while, it starts to get tired. It is fighting and it is losing the fight. Now, going back to the circuit, when the inductor has stored enough magnetic energy and your current is running to its maximum value happily, I remove the battery. All of a sudden, I short circuit it. What I do on the blackboard, I can do remove it, and I do this. So I take away the power supply. What happens? Well, the current wants to die because there is no battery in your circuit, but there is a self-inductor. It doesn't like that the currents are dying. It will have to find it. It doesn't want it to die that easily. So there will be an induced EMF to prevent that. So what you can expect when you had maximum current right here, that your current doesn't go to zero all of a sudden, rather it slowly goes to zero. And for that, I will have to set up a differential equation. And now I don't have to do much. All I have to remove my battery. All I have to remove this V from my differential equation, and I have to solve that. And solution to this differential equation is even easier to solve. This is, I will give you the solution really. The solution I as a function of time is I max again times e to the minus r over L times t, and that's the exponential decay. And check that at time t equals 0, you must have maximum current. Put 0 here, it becomes I max. Check that. If you wait long enough, as t goes to infinity, your current must have gone to 0, of course. Put here minus infinity, it becomes 1 over e to the infinity, and then you get 0. Try it, do it. If you wait L over R seconds, and L over R has the unit of seconds, then your current becomes, I think it was it is 37% of your I max. So I don't have much space there. So what I mean is, first of all, I define this to be my T0 because that's the initial condition. So I redefine here T equals 0. Now I wait L over R second, and my current becomes 37% of I max. Now you may ask why the current is still running. I taken away the power supply. Remember, there was the magnetic energy stored in the solenoid. Now as you remove the battery, the power supply, this magnetic energy is ready to go into electric energy. And that's the reason that you are still getting current. If you had a bulb here, it wouldn't just go instantaneously, boop. Rather it would fade away its brightness slowly. That's what would happen. Now there's one more point that I have to discuss, and because it's really important. Um, and this is there is never any potential drops across the inductors. But you are smart. You take Walter Lowen to the laboratory and you attach a voltmeter across the inductor, and that voltmeter would read some readings while there is still current changing through the circuit. It would read it, and you would interpret those readings as the potential drop across the inductor, and you will say, hey, look, there is a potential drop. Now Walter Lowen would like to remind you that we are dealing with non-conservative electric fields. We are dealing with changing magnetic fields. Now, the integral of E dot dl is no longer path independent. It depends on the path. Again, you are stuck with Faraday. Remember, voltmeter gives you the potential drop across its own large internal resistance. So how do you do that? For practical purposes, take an inductor with a very little resistance so that a little current could flow through my voltmeter. It has a very large resistance, and this one has a insignificant resistance that you can still think of that as the superconducting wire wrapped around, still almost the superconducting wire. So the current is flowing like so, and a little bit of current is going through that voltmeter, and now I'm ready, because through that large resistance that you have in the voltmeter, the electric field will be in this direction. The electric field in the solenoid in the superconductor is 0. And so I have to again use Faraday's law. I will start here and I will go through this. I have to find the closed loop integral of E dot dl around that loop. In going from here to here, it is a little bit of current that is flowing times the large resistance that you have in the voltmeter, and I just call it V. That's the so-called voltage drop, Now I go through the inductor. The integral in going from here to here is again 0 because the electric field is 0. And now be careful, because I was going against the current. This becomes plus L di dt. So you would say, look, this is the potential drop, or I should say so-called potential drop across the inductor. That's what it would read. It is not a measure of a voltage drop across the inductor. It is a measure for the time derivative of a magnetic flux through these surfaces that you have to attach to those loops. And that's really one surface, and that's a crazy kind of surface, staircase kind, and then you have to attach like so, and that's one surface. The integral in going from point A to point B through this route through voltmeter E dot dl is V. But if you go from A to B, E dot dl through this path, it is zero. It is path dependent. It no longer depends on the starting point and the final point. It depends on the path. Once di dt is zero, your voltmeter measures nothing. It reads nothing. I have here a paper published by Voltaire himself in 2002. You might read it. It might help you going through all those stuffs. And it's really well written. You can try it. See you.